All right, everybody, welcome to chapter 9. Let's do a little bit of lecture today on that. So let's talk about chapter 9, t-scores. So today I'm going to give you some foundational stuff. I might talk a little bit about some worksheets on t-scores, or I might do that in a different recording, but I wanted to give you all something today. So let's talk about that. So introduction to the t-statistic. So something that's important is in terms of what our learning outcomes look like today is you want to know when to use a t-statistic instead of a z-score for the hypothesis test. You want to be able to perform the hypothesis test with t-statistics. You want to be able to evaluate effect size by computing Cohen's d, percentage of variance accounted for R2 and or a confidence interval. So some tools you will need. I have worksheets on this. So again, if it makes sense today, great. If not, it's just foundational. Stay tuned. There will be another video after this one, or I will integrate it depending on just how the recording goes, but that's definitely coming in terms of practice. So no worries there, that'll be there soon. So you want to be familiar with sample standard deviation, chapter 4, degrees of freedom in chapter 4, standard error, chapter 7, and hypothesis testing, chapter 8. So the t-statistic, an alternative to z. The sample mean, or m, estimates and approximates the population mean, which is this Greek mu. So this is your population mean, this is your sample mean. I think we've talked about this before a bit. Standard error describes how much difference is reasonable to expect between a sample mean m and the population mean mu. Either this formula or that formula. Very, very similar. We'll walk through that very soon. The z-score, use z-score. The t-statistic is the alternative to the z-score. So you use the z-score statistic to quantify inferences about the population. So we have z is equal to the sample mean minus the population mean over the standard, over the standard error. The obtained difference between data and the hypothesis and the standard distance divided by the standard distance between the sample mean and the population mean. So you want to use that unit normal table, and the unit normal table is totally posted further down where this is posted. So scroll down if you don't see it. And you want to use that unit normal table to find the critical region if z-scores form a normal distribution. Remember, normal distribution is that bell curve. If you forgot or you just want to review that, this is what your bell curve looks like. Remember, it's when it's very symmetrical. This is your bell curve, okay? Basically like that, like it's not skewed. You're gonna have your mean right here in the middle. This distance and this distance would be perfectly symmetrical. Now I'm drawing with the mouse, but I think you get the idea. So anyways, we'll go back to our lecture here. So when the original distribution is approximately normally distributed. So the problem with z-scores, the z-score requires more information than researchers typically have available. It also requires knowledge of the population's standard deviation, which is needed to compute the standard error. Researchers usually have only the sample data available. The t-statistic is an alternative to z. The t might be considered an approximate z. The estimated standard error, SM, is used as an estimate of the actual standard error, theta m, when the value of the standard error, the standard deviation is unknown. Computed from the sample variance or sample standard deviation, this provides an estimate of the standard distance between a sample mean and the population mean. So the estimated standard error uses s squared to estimate theta squared. The formula estimated standard error is equal to, this is your formula, SM is equal to s divided by the square root of n, or s squared divided by the square root of s squared divided by n. When the value of the standard error is unknown, we use the estimated standard error. It is based on variance because sample variance is an unbiased statistic. The t-statistic uses the estimated standard error in place of the standard error. So we're using the estimated standard error instead of the actual standard error. So t is equal to the sample mean minus population mean over the standard, the estimated standard error. The t-statistic is used to test hypotheses about an unknown population where the mean population when the value of the standard error is also unknown. So we're using the estimated standard error, that's the difference between the t-score and the z-score. Degrees of freedom in the t-statistic. Computation of the sample variance requires computation of the sample mean first. Only n-1 scores in a sample are independent. Researchers call n-1 the degrees of freedom. Degrees of freedom describe the number of scores in a sample that are independent and free to vary. Noted it as degrees of freedom. Degrees of freedom is equal to n-1. The t-distribution, the family of distributions, one for each possible number of degrees of freedom, approximates the shape of a normal z-score distribution. It's flatter than the normal z-score distribution, more spread out than the normal z-score distribution, more variability or fatter tails in the t-distribution, use of values of t in place of the unit normal table for hypotheses tests. So this is the distributions of the t-statistics. So you have a normal distribution here at the top. You have your t-distribution, degrees of freedom is 20 right here, and then your t-distribution degrees of freedom is 5. And that shows what that looks like graphically there with that bell curve. So here's the t-distribution with degrees of freedom. Degrees of freedom equals 3, and this is what that looks like in terms of where those cutoff values are, which, like I said, we'll practice in this lecture or the next lecture. So the hypothesis test with the t-statistic, the one sample t-statistic, assuming the null hypothesis is true, t is equal to the sample mean minus the population mean over the estimated standard error, and this is what it looks like notated. All right, so keep going here. So therefore, we have the figure 9.3, the basic research situation for the t-statistic hypothesis test. The known population before treatment was 30 was our mean. We have the treatment and the unknown population after the treatment. So we have 4 steps. First, you want to state the null and alternative hypothesis and select an alpha level. A lot of times we're going to use 0.5. Like I said, we have worksheets in this lecture or the next that'll walk through that a bit. Locate the critical, and there's homework you can do now, but I'll walk you through that, like I said, this lecture or the next. Locate the critical region using the t-distribution table and the value for the degrees of freedom. Calculate the t-statistic. Make a decision regarding HO, which is also the null hypothesis. That's just how it's written or notated. So the critical region in the distribution for A is 0.05 and degrees of freedom equals 8. So here we're not going to reject the null hypothesis. If you get to the cutoff point or further on either direction, this is a two-tailed test, you're going to reject the null hypothesis. So we're going to fail to reject or retain is another way to think about it, or we're going to reject it here. So if you're right here or further, reject it. If you're inside it, fail to reject it or retain it. Either would be correct. Some assumptions of the t-test. The values in the sample must consist of independent observations. The population sampled must be normal. When the sample size is relatively large, this assumption can be violated without affecting the validity of the hypothesis test. The influence of the sample size and sample variance. The larger the sample, the smaller the error. The larger the variance, the larger the error. Large variance means that you are less likely to obtain a significant treatment effect. This reduces the likelihood of rejecting the null hypothesis. So learning check. When the N or sample population is small, less than 30, the T distribution is almost identical in shape to the normal Z distribution, is flatter and more spread out than the normal Z distribution, is taller and narrower than the normal Z distribution, or cannot be specified, making hypothesis tests impossible. So so think about that, maybe pause me if needed. And our answer is when the N is small, less than 30, the T distribution is flatter and more spread out than the normal Z distribution. Decide if each of the following statements is true or false. By chance, 2 samples selected from the same population of the same size, N equals 36, and the same mean, M equals 83. This means that they will also have the same T statistic. True or false? Compared to a Z-score, a hypothesis test with a T statistic requires less information about the population. False. The 2 T values are unlikely to be the same. Variance estimates S squared differ between samples. True. The t statistic does not require the population standard deviation. The z-test does. So measuring the effect size for the t-statistic. Hypothesis test simply determines whether the treatment effect is greater than chance. Chance is measured by the standard error. No measure of size of the effect is included. A very small treatment effect can be statistically significant. Therefore, results from a hypothesis test could be accompanied by a report of an effect size such as Cohen's d. Estimated Cohen's d. The original equation included population parameters. However, the population mean with treatment and the standard deviation are both unknown. Estimated Cohen's d is computed using the sample standard deviation. Therefore, the estimated d is equal to the mean difference divided by the sample standard deviation, and it's notated like this. So this is the sample distribution for the scores in examples 9.2 and 9.3. Here we have the mean of 46, the standard deviation of 4.5 each direction, and our mean of 50 from the null hypothesis. Measuring the percentage of variance explained. An alternative method for measuring an effect size is to determine how much of the variability in the scores is explained by the treatment effect. R squared is equal to the variability accounted for divided by total variability, also written as t squared is equal to t squared plus the degrees of freedom. No worries, we have a worksheet coming up on that too. R2 squared 0.01 is a small effect, R squared 0.09 is a medium effect, and R squared 0.25 is a large effect. Deviations from the mean of 50, no treatment effect from the scores in example 9.2. Original scores, including the treatment effect, are shown right here. No effect, mean is 50. Adjusted scores with the treatment effect removed, no effect, mean is 50. So confidence intervals for estimating the mean. This is an alternative technique for describing the effect size, estimates the mean from the sample mean, based on the reasonable assumption that the mean should be near the mean, the sample mean should be near the regular mean. The interval constructed defines near based on the estimated standard error of the mean, can confidently estimate that the mean should be located in the interval near to the statistic. Every sample mean has a corresponding t-value defined by the equation. T is equal to the mean, the sample mean minus the population mean over our estimated standard error. You can rearrange the equation and solve for the mean. The mean is equal to the sample mean plus TS plus T times the estimated standard error. In any T distribution, values pile up around T equals 0. For any alpha, we know that 1 minus alpha proportion of T values fall between plus T for the approximate degrees of freedom. For example, when the degrees of freedom are 8, 95% of T values fall between plus 2.306 from the T distribution table, alpha equals 0.05. Therefore, we can be 95% confident that a sample mean corresponds to a T in this interval. So this is the distribution of statistics for degrees of freedom is equal to 8. And in this slide that we're looking at right here, you can see the middle distribution, 95% of the T distribution. And then here's our cutoff values. T distribution, degrees of freedom is 8. T is negative 0.2306 or positive 2306 is two-tailed in terms of what we're looking at here. Constructing the confidence interval. For any sample mean with a standard estimated standard error, pick the appropriate degree of confidence, 80%, 90%, 95, 99, 90%. For the social sciences, you want 80% or higher, period, 0.80 or higher, because that's the accepted standard. Use the T distribution table to find the value of T. Degrees of freedom equals 9, and the alpha level equals 0.10. T is equal to 1.833. Solve the rearranged equation, and this is what your rearranged equation would look like. Resulting interval is centered around the sample mean. 90% confident that the actual mean falls in this interval. So we're estimating where the mean is going to fall. It's more of like a range when you think of confidence interval. It's not actually what range is, but it's kind of like a range if you want to think about a way to conceptualize it. Factors affecting the width of a confidence interval. Again, width, like I said, it's kind of like a range, but range is the wrong vernacular. Maybe just think width. Desired confidence level. When more confidence is desired, the width of the interval increases. When less confidence is acceptable, the width of the interval decreases. Therefore, sample size, larger sample, smaller standard error, smaller interval. Sample size, larger standard error, larger interval. So reporting the results of a t-test. You want to report whether or not the t-test was significant. Significant means that the null hypothesis was rejected. Not significant, failed to reject the null hypothesis, or technically retained it. Report the t-statistic value, including the degrees of freedom. Example, t times 8 is equal to negative 2.67. Report the significance level. Either p is less than the alpha, or example, p is less than 0.5, or exact probability p is equal to 0.29, 0.29. Yeah, we have, and don't worry, there's a worksheet on this too that I can walk you through that's in the classroom right now. You can do it on your own, or you can watch for the video coming up. And there's already videos, by the way, that I've posted of everything in the course, I think through at least chapter 15. By the way, you want to work from the bottom up on those posted files if you want to work in advance, or you have any questions that aren't any videos are recorded yet for this course, but there will be more recordings coming soon. So directional hypotheses and one-tailed tests. Non-directional two-tailed test is most commonly used. However, a directional test may be used for particular research situations, for example, exploratory investigations or pilot studies. 4 steps of hypothesis tests are carried out. The critical region is defined in just one tail of the t-distribution. The one-tailed critical region for the hypothesis test in example 9.6 with degrees of freedom equals 8 and alpha equals 0.05. So let's do a learning check. The results of a hypothesis test are reported as follows. T times 21 equals 2.38. P is less than 0.05. What was the statistical decision and how big was the sample? A, the null hypothesis was rejected using a sample of n equals 21. B, the null hypothesis was rejected using a sample of n equals 22. C, the null hypothesis was not rejected using a sample of n equals 21. D, the null hypothesis was not rejected using a sample of n equals 22. Therefore, the results of a hypothesis test are reported as follows. T times 21 is equal to 2.38. P is less than 0.05. What was the statistical decision and how big was the sample? Well, the null hypothesis was rejected using a sample of n equals 21. The null hypothesis was rejected using a sample of n equals 22. So our answer here was B, the null hypothesis was rejected using a sample of n equals 22. Now, if you're not sure how to get there, that's okay. There are worksheets coming up, like I said, this lecture or the next lecture. And they're already there in all those posted files, work from the bottom up. So decide if the following statements are true or false. Sample size, true or false, has a great influence on the measures of effect size. True or false, when the value of the t-statistic is near 0, the null hypothesis should be rejected. So think about that. So these are both false. False, measures of effect size are not influenced to any great extent by sample size. Also false, when the value of t is near 0, the difference between the sample mean and the population mean is also near 0. Remember the dance of the means that I showed you earlier in the previously recorded videos? That is because the sample mean tends to follow the population mean. The standard deviation is going to, of course, drive it. So if you have questions, concepts, anything that you would like to have be clearer, but of course, do ask. And that takes us to the end of that lecture. And that concludes this lecture. There will be some worksheets coming up that will walk through the t-scores a bit. So if you've understood this conceptually, great. If you're still trying to make it make sense, don't worry about the worksheets are already posted, but I will be posting a walkthrough, but there's also a walkthrough already in there from previous lectures. Hope you're all doing great. Cam and Rachel, and please call me if you guys have any questions. Take care, and I will see you live or non-live, or I'll talk to you over the phone or via Zoom. Take care. Hope you guys are understanding everything, and a new video will be coming out very, very soon. And I hope you learned something. Have a wonderful evening, morning, afternoon, whenever you're watching this.